Hello students, in this video we'll determine how to classify linear second-order partial differential equations. Let's consider a function just of two variables to start. Consider a function u of x and y, and the differential operator and the PDE, which is second-order linear, okay, given by it's going to be a uxx plus twice b uxy plus c uyy plus dux plus e, not Euler's number, uy is equal to, I can say plus f u is equal to a function g like this, and g can be a constant, right? Okay, so that's a linear, and let's make it equal to 0, make it homogeneous just to make our life a little bit easier, right? Make it homogeneous. There we go, that's a linear operator. It's a constant coefficient, right? So here a, b, all the way down through f are constants. So it's a constant coefficient equation that's linear, okay? Good. And so what I want to do is the linear terms don't affect the class, right? So what I'm going to do is the following. I want to write this in the following way. I'm going to extract a differential operator from this, and I'm going to use that to classify over here. So I'm going to take this differential operator over here, the second order term. This is called the principal part of the PDE. That's the principal part of the operator L. And let's write L is really a dx squared plus 2b d squared xy plus c d squared y. Let me just do it like this. Let's change the notation a little bit to make our lives a little bit easier, right? Let's make our lives a little bit easier by changing the notation to make it not so sloppy, right? Let's do it like this. Let's do it as a dxx squared plus 2b d squared xy plus c d squared yy. Okay, that's the principal part of the operator. And then we have first order terms over here. Then we have the terms that look like what? We have the d partial x term, we have the e partial y term, and then we have the f identity term over here, like that, identity. Okay, that's our differential operator. And that, of course, this is, of course, the principal part, those terms over there. So I'm going to write this derivative symbolically now. We're going to write it in the following way. We can write that principal part as such. Let's do it like this. Let's write the principal part. The principal part is going to be equal to, I'm going to write as a row vector dx dy, then the matrix A, B, B, C, and the column dx dy. Let's just check that this works over here. If I did four multiplications, it'd be d by dx, d by dy, and then I have a what? I have an a d by dx plus b d by dy, and I have a b d by dx plus c d by dy. If I apply d by dx to this first thing over here, what's it going to give me? It's going to give me an a d squared xx, and then it's going to give me a b d squared yx. Then over here I'm going to have a plus b d squared yx, or xy, doesn't matter, right? And then finally a c d squared y. It works, good, because I have two b's over here. So in other words, I can formally take our principal part of the differential operator and write it like this, okay? Now what's the key feature over here? We know now the matrix AB, A, B, B, C is symmetric, okay? And that means that there exists an orthogonal matrix. There is, by the spectral theorem, there is an orthogonal matrix over here, let's call it O, such that A, B, C, D is equal to O, lambda 1, 0, 0, lambda 2, O transpose, right? And here lambda 1 and lambda 2, lambda 1 and lambda 2 are the eigenvalues of what? Of the matrix A, B, B, C. Excellent. Okay, that's great. And so now, of course, the key feature of this is that now our differential operator really has this form, really has the form d by dx, d by dy, and then this matrix over here, O, and then lambda 1, 0, 0, lambda 2, and then O transpose times this vector over here, d by dx, d by dy, And what this is doing is this is just rotating. What these are doing is these turning into just linear combinations of these differential operators. That's fine, right? That's a coordinate change, and so this is a coordinate change of the standard bases to get directional derivatives in two perpendicular directions, right? So in other words, d by dx dy of applied to O is another differential operator, d, I'll say nu 1 and d nu 2, where nu 1 dot nu 2 is equal to 0 by the orthogonality of the conditions over here. That's great, because now what I'm doing is I just basically rotate the coordinate frames, and now what does my problem turn into? It turns into a perfect equation over here. It turns into what equation? So now the principal part now becomes what? Principal part becomes d squared nu 1 hat, right? Of what? Of u plus lambda 1, of course, right? Lambda 1 plus lambda 2, d squared nu 2 hat of u. That's great, because now it looks like what? If lambda 1 and lambda 2 are positive, that looks like the Laplace equation. If lambda 1 is positive and lambda 2 is negative, that looks like the wave equation. If one of them is 0, if they're both negative, it still looks like the Laplace equation, right? So if lambda 1 and lambda 2 have the same sign, then the problem is elliptic, like the Laplace equation. If they have different sign, then you're hyperbolic, like the wave equation. And if one of them is 0, if either lambda 1 or lambda 2 is equal to 0, then the problem is parabolic, like the heat equation, right? So in other words, how do you classify a second order partial differential equation that's constant coefficients? What you do is you look at the principal part of the equation, the terms that only involve the second derivative. You form this matrix over here, A, B, B, A, B, and that, of course, should be a B, right? So this, of course, is a little typo. Let's change the typo, right? That was just a force of habit. So that's really going to be what? That's really going to be a B and then a C, right? Good. So you look at the principal part of the partial differential operator, and then you compute the eigenvalues of the matrix that corresponds to the principal part. If both of the eigenvalues have the same sign, then you look like the Laplace equation. You're an elliptic equation. If they have opposite signs, one's positive, one's negative, that looks like uxx minus uyy is equal to 0. That looks like the wave equation. So you're hyperbolic. And finally, if one of the eigenvalues is 0, one of these terms over here is gone, and you reduce to something that has a first derivative and only one second derivative, like the heat equation. So you're a diffusion equation. So we've characterized ellipticity, hyperbolic, and parabolic in terms of the eigenvalues of the principal part of the differential operator in constant coefficient form. Thank you very much.